electric potential in a region of space varies as V is By divided by the quantity a squared plus y squared. We are asked to determine the components of the electric field. This problem is another exercise in the relationship between potential and electric field. We remember that differences in potential are given by the integral of electric field, and that electric field components are given by the derivatives of potential. In all these expressions, we see a correspondence between which derivative yielding which component, an x derivative yields an x component of electric field, and so on. And we also recognize that the minus sign is necessary because electric field points from high potential toward lower potential. If we examine the formula that we've been given carefully, we recognize that there are no x's, nor are there any z's in this formula. Therefore, if we attempt to take the derivative with respect to x to create the electric field, we'll have 0. And also if we take the derivative with respect to z to create the z component of electric field, we'll also come out with 0. So both Ez and Ex are 0. The only challenge in this calculation is to take the derivative of v with respect to y because that variable is found in the equation. For simplicity's sake, and because I only tend to remember the product rule rather than the fraction rule, I'm going to write this as by times the quantity a squared plus y squared to the minus 1 power. I'll then be able to take the derivative of this by considering the potential to be a product of two terms. The first term I'll consider to be the by, and the second term I'll consider to be the a squared plus y squared to the minus 1 power. The derivative with respect to y of the potential will therefore be the first of my two terms, by, times the derivative of the second. The derivative of some quantity to the minus 1 power is equal to minus 1 times that quantity to the minus 2 power, and then times the derivative of the interior. The derivative of the interior of this term is going to be twice y. The second term in my product rule is going to be the second piece of the expression times the derivative of the first. The derivative of by with respect to y is simply b. We remember, of course, that electric field is the minus of the derivatives. Therefore, E sub y is minus the derivative with respect to y of the potential. And carrying the minus sign into this expression, we'll have 2by squared divided by the quantity a squared plus y squared, squared minus the second term of b over a squared plus y squared. Although you might be tempted to simplify this expression, that wasn't requested in the problem, and therefore it won't be required. And this completes our derivation of the electric field as a vector derived from an expression of the scalar electric potential.